And this month, we are highlighting many of the technology tests and demonstrations aboard the ISS. The technology we are talking about today actually allows us to have an international space station where astronauts can live and work in a comfortable environment. Lori Meggs is at NASA's Payload Operations Integration Center at the Marshall Space Flight Center to tell us more. Lori?
Breathing in fresh air and drinking clean water are probably some of the things we take for granted here on Earth. But in space, it's a well thought out process that has taken years to develop. We're talking about the Environmental Control and Life Support System, or ECLSS, and that's technology development that helps our astronauts be able to live and breathe in space on the orbiting laboratory. Joining me now is Jay Perry. He has been with ECLSS and the development for more than 20 years. Jay, first of all, tell us about ECLSS. I mean, when we're talking technology development, this is really the pinnacle.
It sure is, and what the Environmental Control and Life Support System does is that it helps provide purified air, good breathing air, and also purified water, and also maintains the temperature and humidity in the cabin. It also helps with recycling resources so that we don't have to take as much from the ground, and it helps us to make sure that the operating the space station or the vehicle is much more economical.
Yeah, it's pretty expensive. We were talking about how much it costs to take a gallon of water to space.
Yes.
You might want to tell folks how much that is.
Well, tens of thousands of dollars just for a liter, and you multiply that by 4, and you can get pretty expensive.
So that's why this technology development is so important. How does it work?
Well, the life support system uses a variety of processes. We use chemical reactions, we use adsorption processes, which an adsorption process is sort of like a sponge. You take the carbon dioxide out with sort of a sponge-like material, and then you can release it and send it to either another reactor or vent it overboard just to get it out of the cabin. We also use a lot of processes that change phases. So just like your air conditioner in your home, there's a similar type device on board the spacecraft in the space station that does the same thing.
And we've built on a lot of history here, from Skylab to Spacelab. This is how we've learned this technology and how it works. But we're looking at the future now. Tell us what we're doing for future deep space exploration.
Yes, Lori, the life support system development has been a progression, going all the way back to the Mercury days and then through to Skylab, Spacelab, Apollo, etc., and then on to space station. In fact, some of the space station processes used on board are legacy from Skylab and the shuttle program, the Spacelab programs. And then what we're looking at as far as being able to go into the deep space applications and destinations, we're trying to build on and learn from what we're learning with operations on the station, how to improve these processes, get to a point where we don't rely on ground-based resupply like we do now, and that way we can go economically to these deep space destinations.
And you actually have a module, a working module that has a lot of pieces in there, a lot of flight hardware or development, test development.
Right. We have a engineering development facility in which we have the carbon dioxide removal equipment, trace contaminant control equipment, carbon dioxide reduction and oxygen generation equipment. And these are varying engineering development fidelities. Carbon dioxide removal and trace contaminant control, for instance, are very high functional fidelity, and also they're very much the same type of fit and form. In other words, the packaging of those pieces of equipment. Our other pieces of equipment are very much engineering oriented, and so their packaging is different, but their function is really, really high, very much identical to what station has.
And you're going to have to learn how to make that packaging even smaller as we go farther, right?
That's correct.
Let's talk about, finally, some of the spin-off technologies, the things that we use here on Earth that have come from the ECLSS technology development.
Okay. We have a variety of both spin in and spin out, actually. Spin in ours is that some of the adsorbent materials and catalysts that we use really come from industry, for pollution control and things of that nature. However, we also have importance as far as, for instance, in water purification. In areas of the world where purified water is a very hard commodity to come by, many of the technologies used on board the station to purify water for the crew to drink have been put on portable platforms to take into these remote areas to provide people with purified water. At the same time, we're learning more and more about having to deal with our carbon dioxide emissions from industry, power plants. And one of the more interesting sources is in producing cement, which we use a lot of on Earth. That's one of the greatest sources of carbon dioxide production into our atmosphere. And so we're working very hard right now to take some of our carbon dioxide reduction processes, starting with what's used on station and expanding out, and applying that to controlling emissions produced by cement manufacturing.
Very interesting work, Jay, and here's to 20 more years of
yes.
you and ECLS.
All right, thank you.
All right, thanks, Jay. To find out more about this and other technologies that are making use of the ISS, join us for our Destination Station Forum on October 27th from the U.S. Space and Rocket Center here in Huntsville. It will be broadcast live on NASA TV and feature experts in many of the technology demonstration fields, such as ECLS. That will be from 9 to 10 a.m. Central Time, again on NASA TV. That's it for us at the Payload Operations Integration Center. Now back to you at Mission Control in Houston.